So in the last video we talked about permutations, which allowed us to calculate the total number of arrangements that we could have from a set of objects, where the order was taken into account. So in a permutation, the order is taken into account. So if we go back to that fruit example where we had 8 fruits, and we selected 3. If we had picked a banana as our first fruit, an apple as our second fruit, and a grape as our third fruit, that counts as one potential arrangement. A second arrangement would be picking the grape first, followed by the apple, followed by the banana. That's 2 arrangements. A third arrangement would be picking the apple first, followed by the grape, followed by the banana. And since we have 3 objects being arranged in 3 spots, we have 3 choices for the first spot, 2 choices for the second spot, 1 for the last spot, which is 3 factorial rearrangements of our single selection of 3 objects. So we have 6 of these rearrangements. Now, what if we ask the question, how many fruit groups we could form? So in this case, order is irrelevant. We do not care about the order anymore. We just want to know how many distinct groups can we form. So one potential group could be this banana, apple, grape. That's 1. If I picked grape, apple, banana, that would belong to the same group, so it doesn't count as a second group. Second group would have to have a new fruit, so it could be a banana, apple, and clementine or orange. So I could have banana, apple, orange, banana, orange, grape. These are all separate groups. And I want to know how many fruit groups can I form of 3 from 8 objects. So what we just described is defined as a combination. So a combination is the possible number of groups that we can form. So a permutation cares about arrangements or order. Now we care about groups. So groups that we can form, and in this case order is irrelevant. We do not care about order. So to answer our question with our fruits, we have 8 fruits, and we're selecting 3. And we want to know how many groups we can form. So we have 3 spots. So let's go back a minute. We know that we have 8 times 7 times 6 possible arrangements. So 8 pick 3 arrangements. If we think about one group, so a group is going to be 3 fruits. So it could be a banana, apple, and grape once again. Each group we said could be rearranged 3, in this case, since we have 3 objects, can be rearranged 3 factorial times. So if we have 8 pick 3 arrangements and we divide by the arrangements of a single group, which is 3 factorial, we'll get the total number of groups. So in this case, the total number of groups is going to be 8 pick 3 divided by 3 factorial, which is equal to 112 groups. Now if we want to generalize this to work with any amount of objects, suppose we have n fruits and we're picking k, so select k, and we want to know how many groups we can form. In that case, we have n pick k arrangements, and then we're going to divide by k factorial, which is the total number of rearrangements we have, and this gives us our total number of groups. If we rewrite this, n pick k is simply n factorial divided by n minus k factorial. That's how a permutation is defined. And so we're dividing this by k factorial, so we can add that at the bottom. This is what we define as a combination. So this is equal to nc for combination k. And just as how we saw a permutation as being n pick k, a combination is usually seen as n choose k. And this is also written in parentheses like this. So all of these are the same thing. So just in case that explanation was a bit too theoretical, we now have an example to solidify your understanding. So we have a group of 5 women and 7 men that are potential candidates for a committee. We want to know how many committees of 2 women and 3 men we can form, and then how many we can form if 2 of the men refuse to work together. So we have 5 women and 7 men that are potential candidates, and we want to form a committee of 2 women and 3 men. Now in this case, let's look at the men specifically. If we picked Mr. A as our first man, Mr. B as our second man, and Mr. C as our third man, that's one potential group. If we picked Mr. B first, followed by Mr. A, followed by Mr. C, that's the same group, and so this is going to be a combination problem. Now if we consider our spots, we have 2 spots for women and 3 spots for men. For the women, we have 5 choose 2 potential groups. For the men, we have 7 choose 3 potential groups. And so for each of these groups for the woman, we have 7 choose 3 groups for the men, and that forms a group for the committee. So the total number of groups is going to be equal to 5 choose 2 multiplied by 7 choose 3, which is equal to 10 times 35, which is equal to 350 possible groups. Now in the case where 2 of the men refuse to work together, we still can form 5 choose 2 groups for the woman. But now for each group of the woman, we have 7 choose 3 spots for the men minus the spots where both of the 2 men that refuse to work together are put together. So that's 2 men, and we choose both of them. From the remaining 5 men, we choose 1. So all of the groups that are of this form, where we choose the 2 men that refuse to work together, if we choose those 2 men and then we choose a third man from the remaining 5, these groups are not allowed. We can't use those anymore. So we have to subtract them from the total number of groups we had earlier. So that's going to be equal to 10 times 35 minus 2 choose 2 is 1, 5 choose 1 is 5. And so we have 10 times 35 minus 5 is 30. So we have 300 groups in that case. So now we're going to talk about an interesting pattern that actually has a connection to the combinations we just saw. So suppose I have a triangle with a vertex up here, and I draw 2 lines to these outside vertices. Then I keep going, but I connect them as follows. So each two vertices connect in the middle on the second row, or in the row below them. And I'll keep going, and technically you could keep going on forever. And now I want to know the number of paths to each vertex from the top down. So only moving down. So if we start at the top vertex, there's only one way we can get to that vertex. From that vertex, if we want to go to the right, we have one path. So there's only one way to get to that right side. If we want to go to the left, we also only have one path. So we can only have one way to get to that left vertex. If we keep going on, all these side vertices have one path to get to them. Now this middle path, so this middle node over here, we have two ways to get to it. We can go this right side and then come downwards, or go to the left side, then come downwards. So we have two ways to get to it. For this second row node, we can go to the right, then come down, then get to it this way. We can go to the left, come down, get to it that way. Or we can travel along this right side and then get to it. So that's three potential ways. And you can use the same logic and you'll find that the left one also has three ways to get to it. And it turns out that the number of paths is the sum of the nodes connected to it. So if I continue this pattern, there's going to be a 1 over here on the side, but I don't have room, so I'll just draw it like that. So if we continue this pattern, starting from the right side, we only have 1 because this is only connected to one node. So 1 plus nothing is going to equal 1. This node is going to have 1 plus 3 connections, so it's going to have 4 potential paths. The one to the left is going to have 3 plus 3 or 6 potential paths, and the one to the left of that is going to have 1 plus 3 or 4 potential paths. And if we keep going and writing these numbers, so 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, this is what we call Pascal's triangle. Now what's interesting is if we call this row 0, this is row 1, this is row 2, this is row 3, this is row 4, and I look at the spot number in each row. So this is spot 0, this is spot 0, this is spot 1, this is spot 0, this is spot 1, this is spot 2, or you could look at it as the index for each row. The number at each index is going to equal the row choosing the index. So the index, I'll put I. So row choose index will give you the number at that spot. So if we look at this 6, it's in the 4th row, so 6 is going to equal the 4th row choose, or combination, and it's in the 1st, 2nd, it's in the 3rd spot, but we're starting at 0, so it's going to be 1, 2. So 4 choose 2, and we can verify that 4 choose 2 is 4 factorial over 2 factorial, 4 minus 2 factorial. 4 factorial is 4 times 3, which is 12, times 2, which is 24. 2 factorial is 2 times 1, which is 2. And 4 minus 2 is 2. Factorial is also going to be 2. And 24 divided by 4, which is 2 times 2, is equal to 6. And this is true for any spot on this triangle. Now we can extend the pattern we just saw earlier to different patterns or to different paths. So suppose for this arrangement where we're starting at node A and ending at node B, we want to know how many paths exist from node A to B, and we'll say we're travel down and right only. So what we do is we know our starting node only has one path to it. From there, to go to any other node on the side, you only have one path, since we can only move to the right or downwards. So all of these nodes on the side have one path. Now we're going to work diagonally from the top to the bottom, since we can only move right and downwards. So starting with this node over here, we add the sums of the node it's connected to. So we'll add 1 plus 1, that'll give us 2. For the node below it, 2 plus 1 gives us 3 paths. For the node below that, 3 plus 1 gives us 4 paths. Moving on to the next column, considering this node, we can move this way and this way. So we have 1 plus 2 paths, or 3. For the node below it, 3 plus 3 gives us 6 paths. For the node below that, 6 plus 4 gives us 10 paths. And we continue with this pattern. Over here we have 4, 10, 20. And continuing to the last row, we have 4 plus 1, which is 5, 15, 35. And therefore, 35 paths from node A to B, traveling to the right and down only. And just one more for practice. So how many paths exist from A to B? Once again, where it can only go downwards and to the right. So this first node is going to have 1, as well as all the nodes on the top side and on the bottom side, since we can only move to the right and downwards. So 1, 1, 1, 1, 1, 1, 1, 1. In the nodes in between, we'll add the sums. So for this first one, 1 plus 1 gives us 2. 2 plus 1 is going to give us 3. 3 plus 1 gives us 4. 4 plus 1 gives us 5. For the node on the right, 1 plus nothing else is connected to it, so we can only have 1. This node on the right, I don't consider, because I can never go from that node back to this node, since that would be moving left, and I'm not allowed to do that. For the node below that, 1 plus 3, since these are the two connected nodes. So 1 plus 3 gives us 4 paths. 4 plus 4 gives us 8. 8 plus 5 is 13. Moving on to the right, once again, 1 plus 1 gives us 2. 2 plus 4 gives us 6. 6 plus 8 gives us 14. Moving on to the right once again, 1 plus 2 gives us 3. 3 plus 6 gives us 9. And 9 plus 14 gives us 23. And moving on to the last column, we have 1 plus 3 gives us 4. 4 plus 9 gives us 13. 13 plus 23 is 36. And this bottom node at B is going to have 36 plus 13, or 49 potential paths. Therefore, 49 paths from A to B, moving down and to the right only.